Assalamu alaikum. The objective of this video is to know how to control the capacitance of the capacitor. We have said that the capacitance is the ability of a capacitor to store electric charges. In this animation, we are going to see what are the factors that affect the capacitance in the case of a parallel plate capacitor. What do we mean by a parallel plate capacitor? A parallel plate capacitor is made up of two parallel plates which are separated by an insulator. In this case, the insulator is the air. Here I have a generator which is connected across an initially neutral capacitor. In order to charge the capacitor, I'm going to increase the voltage of the generator to 1.5, for example. Now the capacitor is charged. It has one positive plate and the other one is a negative plate. In order to see what are the factors that affect the capacitance, I am going to vary or change these two variables. The first variable is the distance separating the two parallel plates, or the distance of separation. I can increase it and I can decrease it. The other factor is the area of the plates, or the common area of the plates of the capacitor, which also I can decrease it, or I can increase it, or I can decrease it. These two factors affect the capacitance, but how? Now I'm going to increase the distance of separation between the parallel plates, and you are going to look at the capacitance here of the capacitor to see whether it is increasing or decreasing. Look carefully. I'm increasing the separation from 4.2 millimeters, where the capacitance is approximately equal to 0.25 picofarad. I'm going to increase it till the separation is 10 millimeter and the capacitance is 0.11 picofarad. Notice that the capacitance decreases when the separation increases. Then the separation and the capacitance are anti-proportional. If I increase the plate area, what happens to the capacitance? Let us see. The plate area is equal to 120 millimeters squared and the capacitance is equal to 0.24 picofarad for this area. Increase the plate area and look carefully on the value of the capacitance given. The value of the capacitance increases till 0.70 picofarad when the plate area is equal to 350 millimeters squared. Then these two factors affect the capacitance in such a way that if the separation or distance of separation between the two parallel plates increases, then the capacitance of the capacitor will decrease. If the common area of the plates increases, then the capacitance increases. So a parallel plate capacitor, which is mainly made up of two parallel plates separated by a dielectric or an insulator, has mainly two factors that affect its capacitance, which are the common area of the plates and the distance of separation between the plates. This formula here gives the relation between C, A, and D, where the capacitance C is given by A divided by D multiplied by this constant here. This constant is called the dielectric permittivity of the insulator, which is inserted between the two plates of the capacitor. You can remember from the previous animation that the area and the capacitance are proportional. The distance of separation and the capacitance are anti-proportional. Note that the unit of the capacitance in this formula is farad, that of the area is meter squared, and that of the distance is meter, and that of this constant here is farad per meter. What is this constant or the third factor that is affecting the capacitance? This factor is called the dielectric permittivity, which is given by this letter and pronounced by epsilon. The dielectric permittivity is defined by the permittivity of the dielectric as a physical property which describes the response of a given medium to an applied electric field. Each medium has a specific permittivity. So the permittivity that we are talking about is a characteristic of any medium. So the capacitance of a parallel plate capacitor is given by C is equal to epsilon multiplied by the area divided by the distance. As the epsilon increases, then the capacitance will increase. When the epsilon increases, that means the insulator used is a very good insulator. Epsilon 0, which is equal to 8.85 times 10 to the power minus 12 farad per meter, is the permittivity of the vacuum or air. In case the dielectric used inside a capacitor is the vacuum or air, then its capacitance is defined by C0, which is equal to epsilon 0, the permittivity of vacuum or air, multiplied by the area divided by the distance d. Now I am going to define another variable which is called the relative permittivity of dielectric material. The relative permittivity is given by epsilon r, where epsilon is equal to epsilon 0 multiplied by epsilon r. Epsilon r is strictly greater than 1. The capacitance of a capacitor for any dielectric material is given by C is equal to, instead of epsilon, I'm going to insert or substitute by this equation. Epsilon is equal to epsilon 0 times epsilon r. I'm going to substitute it here. Then the capacitance C will be equal to epsilon 0 epsilon r times A divided by D. Now, if I want to substitute this equation here in this formula, then I will get epsilon 0 times A divided by D is equal to C0. Then the capacitance C is equal to Z0 multiplied by epsilon R. In this table, we are going to see some examples about the relative permittivity of some materials. For example, the relative permittivity of vacuum is equal to 1, and you can check it using calculation. Of the air, it is approximately equal to 1, and that for water is equal to 78.5. Application number 4. The two armatures of an airplane parallel plate capacitor are spaced by d is equal to 1 cm and have a common surface area S is equal to 1 decimeter squared. Part A, calculate the capacitance of the capacitor, and in part B, I have to deduce capacitance if we introduce another dielectric between the plates, which is the paraffin of epsilon r is equal to 2.2. In part A, I have to use this relation, which is C0 is equal to epsilon 0 S divided by D. Sometimes we use A for the area and sometimes we use S, and the final answer will be 8.85 times 10 to the power minus 12 farad. In part B, I have to use the formula, which is C is equal to C0 multiplied by epsilon R, which is equal to 19.49 times 10 to the power minus 12 farad. Don't forget that we have to convert to the SI units. A capacitor cannot tolerate any voltage, so we have to define the breakdown voltage, which is the maximum voltage that can be applied across the capacitor without causing a destroy or a damage to it. The breakdown voltage depends on the nature of the dielectric and on the distance which separates the two armatures. A charged capacitor stores electric energy which is released during discharging. But how can we calculate this stored electric energy? This energy is given by the symbol, which is W. Here we use a symbol W for the energy, which is equal to half Q times U. If we substitute in this equation instead of Q, Cu, then we will get W is equal to half Cu squared. And if we substitute in this equation instead of U, Q divided by C, then we will get this equation, which is W is equal to 1 over 2 Q squared divided by C. These three equations are used to calculate the stored electric energy for a capacitor. Don't forget that I have to use the SI unit for all the variables. Remember that the SI unit of the energy is joules. Application number 5. A capacitor of capacitance C is equal to 49 microfarad is connected across a generator with EMF E is equal to 12 volts. Part A, I have to calculate the charge Q of the capacitor. I have to apply this formula to get 5.64 times 10 to the power minus 4 farad. I have to convert from microfarad into farad using 10 to the power minus 6. And in part B, I have to deduce the energy stored in the capacitor. In this case, I can use one of the three formulas that we have mentioned. Why? Because I know C, I know V, and I know Q. Here I've used W is equal to half Q times U, which will give 3.384 times 10 to the power minus 3 joules. You are going to discover more about capacitors in the other videos. Thank you for watching.